Assalamualaikum warahmatullahi taala wabarakatuh and very good evening to everybody. First of all, my name is Zainab Mohamed Yusof and today I will present my paper ID number 85 on the title of Modeling of an Embankment Failure using Flow-3D, and I'm from UTM Skudai. Okay, this is the table of the content that I will present today. So we go first on the introduction. Okay, what is the embankment dam? The embankment dam, some people call it as a dam, levees, dikes, and a barrier. And this is the hydraulic structure, and it widely used in flood defense, power generation, water supply, transportation, and the sediment retention. And this hydraulic structure will fail and will be breached due to the several events. For example, we have the overtopping flow over the structure, the piping and the internal erosion, and what we afraid of having this phenomena is due to the flooding, losses of the life, destruction of the properties, and the interruption of the services. This is the case of the Titan dam failure, and it caused a million of the damages and death. Okay, so why we need to study this? It is because approximately 34% of a dam failure is caused by the overtopping, 30% by the foundation defect, and 28% by a piping. And the most common causes of the embankment failure are the overtopping and the internal erosion. And there's a many study conducted saying this statement. And Relson in 1987 indicates that there are approximately 97,000 dams in the US have the potential for the overtopping, and leading cause of embankment dam failure worldwide is overtopping. Okay, so the objective of this study actually is we have three objectives here. The first one is to determine and compare the hydrodynamic parameters. We need to plot the breach failure pattern. Okay, we set a case for this kind of the analysis, and to analyze the shear stress on the embankment, hydrostatic pressure, and the free surface profiles during the breaching process. Okay, so the scope of the study, actually we have three parts. The first one, we will do the simulation of the model using CFD model. We call it as a Flow-3D. And the software utilized, okay, will solve the Navier-Stokes equation in fluid dynamics coupled with the sediment scouring properties of the soil. And then we will manipulate the data. So in terms of the sediment sizes of the embankment with a constant inflow rate. And then the last part on the analysis. So there are a few parameters that we will be test. Okay, what is the overtopping flow and how it works, and what is the failures? Okay, so overtopping flow is a result of the insufficient spillway capacity for an event of extreme flood. Extreme flooding which cause water level to exceed design criteria. Okay, and then how it happened? Okay, because of course because of the uh, 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 heavy rainfall. Okay, we have the extreme rainfall event, and due to the overtopping, so it will introduce the tractive shear stress on the downstream surface and also at the crest of the embankment. The erosion process begins at a weak spot where the tractive shear stress exceeds a critical resistance that keep the soil material in place. And what are the failures? So we can see the initial breach happen. Often basically it will look like a V shape and become larger as the erosion progresses. Before we model, okay, the breaching embankment, so we need to know what is the characteristic on what the behavior of the embankment when it interact with the overtopping flow. This is actually studied by the Wah in 1998. Okay, to study the characteristic of the embankment failure for the granular soil, sand, and small gravel. Okay, so in this study, we will be look into the effect or the changes of the geometry of the embankment geometry parameter in terms of the bridge depth, the stop width, average bridge width, bridge bottom, and the bridge slide slope factor. So, okay, and there are a few parameters for the hydrodynamic parameters that we will analyze in terms of the peak outflow rate or peak hydrograph of the uh, bridge outflow and the failure time. Okay, before we do the model, when we run the model, we need to set up the model. Okay, there are five things or five terms that we need to set up first. The first one on the general setting, and then the meshing of the model, the boundary condition of the model, initial condition, and the prop and the flux surfaces. A prop and the flux surfaces is useful for to analyze the specific point that may interest in our study. Okay. So this is the model setup using Flow-3D. Okay, the first one, we need to prepare the model geometries and its dimension. We do it in using the AutoCAD 3D. Okay, this is the size of the embankment. Okay, and then we have to put notch here. So the notch here, we have the size of the notch, basically to initiate the bridge. So that we have a constant bridging. And this is the mesh size. Okay, so before we run the model, so we need to set up the mesh size. All right. Okay, for the general setting, so we set for the model computational model computational finish time, the model physics, okay, and the fluid properties. Okay, in this setting, we set the sediment diameter in the sediment scour model. So and then we do the meshing with the uniform size of 0.02 meter. Okay, so very small. Okay, so the finer the mesh, okay, so means we will get more accurate result. So the mesh is the act of the creating mesh, which is subdivision of the continuous geometric space on a geometry. So it's quite important to have a very small mesh. All right, and then we go for the, and then we set for the second boundaries condition. So here we use, we define the condition, the boundary condition for the inflow here. Okay, we set for the volume flow rate. Outflow here, we set for the outflow. Okay, and then top of the model, we use as a symmetrical. So I mean it's opening to the air. And the bottom one of the channel, okay, we set it as a wall. Okay, this is the, sorry. Okay, this is the boundary condition setup. Okay, so as you can see here, we have the inflow and the outflow. At the inflow, we set up as a volume flow rate boundary, and the outflow we set up as a outflow. Okay, the side, left and right, we set up it as a symmetry, means we open it to a wider embankment. And then on the top here, on the top of the channel, we set it as a specified pressure. Okay, so that we allow for the interaction between the water and the air, depending on the height of the water surface. Okay, and the equation govern the motion of the fluid flow at the initial time and the boundary. Okay, then we set up for the initial condition. Okay, initial condition is the initial state of the solution for transient fluid flow problems that we need to know to find a solution. So meaning we define the starting condition in the simulation. In this case, we define before the simulation started. So we define the height of the water surface, so to reduce the computation time. So Here we set it as a t equals to 0 before we start the simulation. Okay, and the last one is on the probe and the flux surface. Actually, this is for the analysis. Okay, so the probe and the flux surfaces are the point measured tools to measure the quantities that flow through the model. Okay, and then here we got basically three panels here, three plate here. So at the upstream, at the middle of the embankment, and at the downstream of the embankment. So we can see what happened at the middle of the embankment and before and after the embankment. So it's depending on the parameter that we set up to analyze. Okay, this is the result and discussion. Okay, the first one we talk on the bridge outflow hydrograph and its failure time. So these are the graph that we obtained, and we can see if you compare the sediment size, okay, between the finer, the medium, and the coarser sediment. Okay, we can see that the coarser sediment produce larger peak of flow hydrograph. Okay, so this is the one. Okay, the single dotted one here. Okay, is for the coarser sand, which the size of the sediment is 0.8 millimeter. As you can see, it gives the higher peak outflow. Okay, and then it has the high erosion rate. Okay, this you can see from the slope due to the sediment is loosely packed as compared to a finer sediment where the particle is much closer and interconnected. Okay, meanwhile, in terms of the failure time, for the coarser embankment, it has a shortened failure time. And the larger the peak outflow hydrograph, okay, means that embankment collapse earlier compared to the finer and the medium embankment sediments. Okay, this is in terms of the bridge width and the bridge depth. This is the bridge width, okay, and this is the bridge depth. Okay, so as you can see here, the embankment with a coarser sediment produce fast erosion to achieve the bridge width and the bridge depth compared to a smaller sediment sizes. That means more erosion for the coarser sediment occurs. Okay, this one in terms of the bridge growth. Okay, bridge growth means the growth of the bridging for the horizontal and the vertical direction. So again, as you can see here, the coarser sand, which is 0.8 millimeter diameter, the bridge side was the largest at time interval of 60, 80, and 100. So the dotted one represent for the coarser sand. So the finer sand of 0.1 millimeter diameter has the smallest bridge size at the time of the interval 60 second, 80, and 100 second. Okay, so after that, we try to model for a special case for whereby the border input that we use for the sediment size is 0.4 millimeter, where the flow rate remains same, 0.012 meter cube per second. Okay, this is the profile of the bridge or the failure line. So during the breaching time, okay, we start from the 0 second until 140 second. So this is the trend or the profile of the bridge. Okay, so as the bridge depth increases, the height of the embankment reduces. The downstream slope angle of the embankment also decreases. Okay, the fifth analysis is on the hydrostatic pressure and the free surface profile during the breaching process. Okay, this is a snapshot of the results, okay, in terms of the hydrostatic pressure with regards with the free surface profile. Okay, in hydrostatic pressure analysis, as you can see here, there is an increment in bottom pressure from T equals to 40 to T equals to 60. So this is due to the rising in water elevation during the overtopping flow. Since the erosion rate of the moment is still slow, the embankment height shows little change with the result in hydraulic jump and increase in the water elevation. At the downstream, we can see a slightly the hydraulic jump happen because of the hydrostatic pressure. At t equals to 80 seconds, the hydraulic pressure at the bottom decreases as the embankment height decreases due to the erosion from the result of the lower water elevation. And as the erosion continues, the hydrostatic pressure at the bottom continues to decrease as the embankment height decreases until the water level becomes constant, indicating the breaching is complete. So after 3 equals to 120 seconds, we can see the constant start to have a constant water surface. And this is the result for the shear stress. Okay, so as we can see, the maximum shear stress happened at t equals to 80 seconds. And this we can understand that at t equals to 80 seconds, actually the flow has reached the maximum flow, where the shear stress recorded at this time is 9.87 Newton per meter square, and then it start to reduce, okay, after the flow reach the maximum, and then continues until the end of the simulation, where the shear stress here becomes 4.91 Newton per meter square. All right, this is the relationship between the shear stress and the bridge width and also the bridge depth. So we have plot the shear, okay, along the embankment here, okay, for the time of the bridge, breaching. So as you can see here, so the maximum shear happened at t equals to 80 seconds, and the top bridge at that time is 0.85 meter, and for the depth is 0.2 meter, and it will continuous bridge until the flow becomes stable at the downstream. So here we have the relationship between the shear stress and the bridge width, and the shear stress with the bridge depth. The shear stress during the breaching increases, then decreasing after reaching the peak value, and the bridge depth increases along with the increment of the shear and keep constant after reaching the maximum shear. You can say that the peak outflow hydrograph is higher and has shorter failure time for embankment with larger sediment size. Means if we have coarser sand, means it will give the higher peak hydrograph, lower failure time, means the erosion become fastest, and we have the increase of in terms of the bridge width and the bridge depth and the shear stress as well. The embankment dam with large sediment sizes will have larger bridge depth and the width. The bridge depth and the bridge width also show an increment when the shear stress increase. The hydrostatic pressure at the upstream is greater than the hydrostatic pressure at the downstream, and the surface of the embankment during breaching keeps on eroding, and change shape will lead to a variation of the to the flow depth. Okay, I think that's all for my presentation. Thank you very much for your attention.